Log on, tune in, find out. Another good idea from Cambridge.
Okay, it's off. So I came last time to the following place. So if I have G as a complex reductive algebraic group, then, well, I said that a real form of G up to equivalence was the same thing as an automorphism, let me call it theta, of G of order 2. And I should be careful, as Cedric was, what one is allowed. Sorry? Well, one corresponds to the compact form, yes. I'm now going to write K for the fixed points of theta, which is another complex reductive algebraic group. This one I want to be connected. This one is maybe not connected. And this group has the connection between these two things is that if I look at the group of real points and take, well, all right, a maximal compact subgroup, then the operation that I explained of complexification of a compact group carries this maximal compact subgroup to this algebraic group. And what in this setting over here, so I've changed notation. So now G is the Lie algebra of G. This is complex reductive. I was using a subscript C before. And now over here, I have GK modules. And these have something to do with, with reasonable representations of this group G of R. I talked about this at some length. The connection is complicated, but at any rate, what I want to do now is study these things. And in order to do that, this course was supposed to be about the relationship between this representation theory and the geometry of Schubert varieties. So what I should do is tell you how to connect these to the geometry of flag varieties. So here's how this works. So let me, I think maybe it's safe to write B for the variety of Borel subgroups. Of my group G, so this is projective algebraic variety. And I'm going to simplify things. I want to restrict attention to representations on either side. Well, in which? So I have U of G. This is the universal enveloping algebra. And this has, all right, Z of G, the center. So this is a polynomial algebra in the rank of G generators. So I want to look at representations in which the center of the enveloping algebra acts as it does in the trivial representation. So that's, of course, a very restrictive condition, but what happens is this is essentially the hardest case. I'll just say a couple of words. In any irreducible representation of a Lie algebra over the complex numbers, the center of the enveloping algebra has to act by scalars. This is one of the sets of scalars by which it's allowed to act. And what I'm saying is, if you study representations in which the center acts by some other kind of scalars, then it's easier than this case. So I'll just say this to simplify the exposition. So yes. Well, I mean.
When your character is more regular, there is some pathologies anyway. So I wouldn't.
That's already. Oh, I mean, you're talking about the general case, but I'm not. So you see,
I just argue it's hardest case.
I know. I mean, I've been doing this for this is the hardest case. There's no doubt about that. I mean, it's not to say that everything else is trivial, but this is the hardest case. So how do you deal with this case? So of course, the group G acts on B, and this is algebraically, and as a consequence, you get a map from the universal enveloping algebra of G to so this is by definition the algebra of algebraic differential operators. On B. So Ivan didn't define these this morning, so I won't define them now either. So that's fine. You of course you know that B is a projective variety, and what you know about projective varieties is that there aren't many algebraic functions on them. The only globally defined algebraic function is the constant, are the constants. But the situation is better for differential operators. The only zeroth order differential operators are the constants, but the action of this group provides some interesting vector fields on B. Actually, yeah, it provides all of the, well, all right, let me just say that you have this map, and the proposition of Beilinson and Bernstein is that the kernel of this map from U of G to these differential operators is, well, it's not surprisingly a two-sided ideal. It's the two-sided ideal generated by the kernel of the center of the enveloping action, the center of the enveloping algebra action on the trivial representation. So exactly the ideal that I'm assuming to act by zero over here. And what's also true is that the map is surjective. That's the first part is very easy. Well, the second part isn't that hard, but it's the second part which is entertaining. So what this tells you is that this condition, I'll call this trivial infinitesimal character. That's so what this proposition says is that G modules with trivial infinitesimal character are the same thing as modules for this algebra of differential operators on B. And what Beilinson and Bernstein understood was that you can construct these using geometry on B. So, for example, if you take Z inside B, well, any closed subset. So closed can be just in the classical, in the what's the word, the calculus topology, okay. I mean, this doesn't mean Zariski closed it. I mean, this could be the equator in CP1, or so if you take a closed subset, you could define M to be all the distributions in the sense of Schwartz on B with support in Z. That makes perfectly good sense. And one of the things you can do with Schwartz's distributions is differentiate them. And differentiation doesn't change support. This is a D of B module. And so well, say there's a large supply of closed subsets of the flag variety. We're interested, however, in GK modules. What we want are G modules equipped with an algebraic action of K. And so the well, let me just say what the rough idea is. This is a way to get sort of random modules for these differential operators. So G modules with a certain infinitesimal character. If we also want to have an action of K, what we should do is use the action of K on B. So the rough idea is to use a subset Z inside B that's K stable. And then, well, this space of all distributions will have an action of K, but you'd have to take the subspace of all the distributions on which K acts algebraically. So, for example, if you take a delta function at a point, something like that, and move it around by K, you'll get delta functions at other points, but you'll get an infinite dimensional space that way, usually. So what this means is you end up not being allowed to use things like delta functions at points. You need something more like an integral over a K orbit, a distribution that looks like that. That's stated very vaguely, but at any rate, I can say what the theorem is that they finally prove. Says that the irreducible GK modules with trivial infinitesimal character are in one-to-one correspondence with irreducible K-equivariant local systems on orbits of K on B. So this, to say, this theorem is not terrifically difficult. It's the amazing thing is the idea of writing down, well, it's an old idea to write down this map from the enveloping algebra to differential operators, but to realize that the map is surjective, that's a very powerful feature. And once you have this in hand, it isn't, as I say, incredibly difficult to prove this. Well, let me do an example. So let's do it here. So if I start with SL2C and the real group SL2R that I talked about yesterday, or Tuesday, the maximal compact subgroup here is SO2, so this is these matrices cosine theta, sine theta minus sine theta, cosine theta. And the corresponding, well, the complex version is SO2C. Well, so I could write cosine z sine z for z a complex number. Here theta is real. And well, the involution is the inverse transpose involution. And so in this setting, the flag variety can be identified with lines in C2 with CP1. That's what CP1 is. And what happens is that there are three SO2C orbits on these lines. The fact that there are three orbits is essentially Witt's theorem. Because when I talk about SO2, I'm talking about a quadratic form on a two-dimensional vector space, and I want to know what a line can look like with respect to a quadratic form. Really, Witt's theorem says that there are two O2C orbits, but that's all right. So what the orbits are is the isotropic line, the multiples of 1 and I. There's another isotropic line, the multiples of 1 and minus I. And there's the rest, which looks like, so if I take the complex projective line and remove 2 points, what's left is a punctured plane, C cross, and this is SO2C divided by plus or minus 1. Okay, so that's the orbits. And so there are there are 4 irreducible GK modules with trivial infinitesimal character. So according to this Balance and Bernstein theorem, there's something corresponding to this line, this is just a point, and so the only choice I have is to put the trivial local system on a point. And this corresponds in some sense to an irreducible Verma module. Which has SO2 weights, what are they, -2, -4, well, let me make it +2, +4, +6, like that. There's this other isotropic line with its trivial local system, which looks exactly the same, and this also corresponds to an irreducible Verma module, but this time going in the other direction with SO2 weights -2, -4, -6, like that. I've drawn this very unclearly. This rest, this punctured plane, has 2 irreducible local systems, equivariant local systems. I mean, if you just look at local systems on the plane, and they have to do with representations of the fundamental group, which is Z. You can do anything you want, but we want SO2 equivariant, so they just have to do with representations of the component group of the stabilizer. So representations of this ±1 stabilizer divided by its identity component. That's so Z mod 2Z. That's what's going on here. And if we put the trivial local system, then the representation we get is the trivial representation with SO2 weight 0. I haven't described this representation, but you can work it out as an exercise. And then there's a non-trivial local system. And this turns out to correspond to a representation with SO2 weights ±1, ±3, ±5, like that. It's not a Verma module. The weights are infinite in both directions, but it's a perfectly good representation of the Lie algebra that you can write down. So that's a list of the 4 irreducible GK modules for this group SL2R, trivial infinitesimal character, and the correspondence with these local systems. Okay, so what's going on now? So I should say I don't want to give inappropriate credit to Beilinson and Bernstein here. I should, well, it's not going to show if I write here, but I should say that the classification of these irreducible GK modules is due to Langlands in 1967. So this is around 1980, I forget. So it isn't that Beilinson and Bernstein were the first to figure out a list of what these things are. It's that they phrased the answer in a way that it hadn't been phrased before. So, you're right. I should add, Langlands did the reduction to tempered. Harishchandra nearly, had come very close to classifying tempered representations, but that was only finished by Knapp Zuckerman and Knapp Stein, and this was all cleaned up around 1975 or so. There are a lot of little details, which mostly have, which don't occur in the setting of, I'm talking in a sense about trivial infinitesimal character, and for trivial infinitesimal character, none of those complications arises, and it really was clear from Langland's results. Okay, so what I wanted to do, there's so many things to talk about here. So what I want to do, I think it's relevant to say, how do you list these pairs of an orbit of K on B and a local system? So when you talk about the category O and say that modules are classified by their highest weights, part of what you want to know is how to make a list of all possible highest weights, and that's easy. You have some weight lattice where your weights live, and that's the answer. So in order for this Beilinson-Bernstein theorem to be of that quality, you want to have some way of getting your hands on these gadgets. I know one thing that I wanted to do was make two advertisements. And so the first advertisement is that you let's say it like this. That's the answer. There's some software which was written by Foucault-Duclos and is being ever expanded and improved by Mark van Leuven. And the software is called Atlas, and it's available at www.atlas.org. leegroups.org. And this software is written in C++, and if you put it on a Unix system and say make, it'll compile, and anyway, there are instructions for all those things. And if you start up the software, it says empty, and if you type block, you will get some list of pairs like this. So in a sense, you don't need to know. Somebody else knows. Somebody else figured it out. So that's one of the advertisements that I wanted to make. The other advertisement that I wanted to make was, since this is an audience that at least 2 weeks ago liked the idea of workshops, so I should advertise that there's a workshop which is at the University of Utah, and it's July 20th to 24th, 2009, and I can't remember the title now, but I did write down the address for that. Yes. It's hard to remember. Workshop. And so this workshop is like the one here, aimed at especially at graduate students, young postdocs. There's some funding available, so you should, if you have any interest, go and sign up. I'm afraid that in Utah in the summer, we don't have the gift of the nice securing clouds that are present here, but if you can tolerate a little sun, then it's a good thing to do. So those are the two advertisements. So how do you do this really? So I want to, it's useful to back off a little bit and ask, how do you list the possible Ks? So here's the story. So so many people have more or less mentioned that this G-connected reductive algebraic group over C, it's been implicit in many of the lectures that such a thing is specified by what's called a based root datum, which is a lattice, the dual lattice, a finite subset, there, and a bijection there, and well, so well. So I'm not going to write down what all of these things are, well, maybe so if we have a Borel subgroup, and H maximal torus, then this X upper star is the lattice of characters of H, and so R is the non-zero characters of add H acting on the Lie algebra. G and R plus is the same thing for B and so on. So probably know how this all works. So the point is that this information over here is wonderful computer information. I mean, lattices are nice to put into computers. An element of a lattice is a string of integers. You can put it in your computer without fear of contradiction. So this is writing down a connected reductive algebraic group means writing down, well, you decide the dimension of the lattice, and you decide it's going to be Zn, and you write down a finite set of strings of integers that are supposed to be the roots. Then you've sort of specified your connected reductive algebraic group, and what I want to describe is how you describe K and these orbits and these local systems just in terms of these lattices. So it's fine to say that these things determine the group, but in order to be able to do the computation, the idea is to say how you, just in these terms, solve some problem over here. So that's what I'll try to do. So here's the story. Okay, so what I'm looking for an automorphism theta of G of order 2. So the sort of the functoriality of the structure theory, when I write this arrow, this is this is everything ever written about reductive algebraic groups. There's a lot going on in here, but this arrow here, what that means is that theta gives rise to an involutive automorphism that I'll call delta 0 of this based root datum. So what this means, this delta 0 is, well, I mean, if this X upper star is secretly Zn, then this delta 0 is an n by n matrix of integers. Delta 0 squared is 1, but it's also supposed to have a bunch of other properties. It's supposed to preserve R plus and things like that. So when you do this, you lose information. This is algebraic groups up to sort of inner automorphisms that give rise to these lattices. So when I go from this involutive automorphism to the automorphism of the base root datum, I lose some information, but at any rate, I can do that. And so what I want to do is write gamma, this is 1 delta 0, this two-element group. And this acts on G while preserving all the things that I used to make this B and H, and the thing that I haven't said is a pinning, and so I get what I'll call G gamma, just the semi-direct product of of G and gamma. So that makes good sense. And now, now what's more or less clear is that an automorphism of G that's inner to this delta 0 is the same thing, so always algebraic. This is the same thing as an element of this coset G delta 0, the non-identity coset in here. No, this is a theorem acting on G by conjugation. Well, it's a coset of the center of G in there. So well, I mean, I didn't define inner. I mean, I should have defined inner in advance, yeah, but anyway, I could have started with any kind of automorphism of G and gotten this automorphism of the base root datum and done something like this. And so what happens is that these G conjugacy classes of these theta, these involutive automorphisms of G, this is the same thing as, well, a G conjugacy class of these involutive automorphisms is the same thing as a G conjugacy class of, well, let me say almost twisted, well, I don't know where to put the words, almost twisted involutions. So X in this, so this condition is just, well, the whole thing. That's what this means, is that the square of x should be in the center of G. I probably shouldn't use the word twisted. I mean, if I write x is G delta 0, then it's G, which is the word twisted has to do with G, because G is satisfying some condition like that's the reason why you say twisted. And almost is that it's the center instead of being one. Okay, so that's a lot of nonsense, but so this doesn't make it clear that I've made anything computable. This is just rephrasing the situation. So let's So let me write n for the normalizer in G of this cartan. I'll remind you that I have this, well, H inside B and inside G, and here this delta 0 is acting. So the statement is that every conjugacy class of these almost twisted involutions has a representative of the form H times delta 0 for H in H, and it's unique up to conjugation by n, and this is, again, there's almost no content to this statement. It's essentially the statement that any element of the group can be conjugated into, well, any semi-simple element of the group can be conjugated into this maximal torus. You have to worry a little bit about the twist, but not much happens. So well, I just want to say that it's easy to write the conditions on H to be an almost twisted involution, and well, I don't want to go much further in this direction. So more or less, this is kind of an outline of how you list the possible Ks. Let me, maybe I'll state a theorem that sits next to this. So the version of this theorem which Jeff Adams and Foucault Duclos worked out says that these pairs, some choice of x in this g gamma minus g x squared in the center, and I mean, I'm allowed to consider inner if I wanted to consider inner automorphisms, I would have chosen delta zero to act trivially. I mean, that's which is one of the cases. Yeah, I mean, it's certainly allowed, but it's convenient to have it separated like this. So this kx, the stabilizer of x in G, a kx orbit on the flag variety. So a pair of these things up to conjugation by G is the same thing as an element n in this n, this normalizer in G of H, with the property that, well, this is in the center up to conjugation by, I think I want to, well, yeah, sorry, let me keep the factor because I want to conjugate this product. So it's just this coset of the normalizer and everything up to conjugation by H. So essentially, this is Weyl group calculations. That's it's a little bit worse than that because the Cartan is here a little bit, but this condition that the square is in the center means that not much can happen from the Cartan. In fact, the hard calculations go on in something called the Titz group. That Titz was studying how the Weyl group, the extent to which the Weyl group of an algebraic group embeds in the group, and he made a place which is just designed for doing these calculations. So this is well, what I want to say is that this is a sort of computationally effective list of these irreducible GK modules. Well, I haven't, sorry. Yeah, you're right. Well, let me just say the orbits. Yeah, the local system isn't here yet. That's another small issue. It's not very difficult. What I want to do tomorrow is talk about how to identify unitary representations in these lists. So, well, I haven't completely made a list. I only made a list of orbits, but nevertheless, I'll try to talk about this question. So I'll stop there.
Are there questions, remarks? Can you indicate how you get this element in the normalizer corresponding to orbit?
Sure. The idea so I have this theta, which is conjugation by some something like this, and so there's this fixed force K naught, and so I have I have some orbit like this. So this is another Borel subgroup. And what I want to understand this orbit. So what I do is I conjugate by G. I conjugate B back to this sort of base Borel subgroup. Sorry, no, I haven't said this properly yet. So the stabilizer is the intersection of K naught with B. How do I say this? Yeah, I'm saying this badly. I mean, this is x0. So what happens is there's another Borel subgroup. This is the conjugate of B by this x0 that's somehow relevant here. And what you have to do, I mean, the intersection of these two things is x0 stable, because the square of x0 is in the center. So if I conjugate by x0, I come to translate by the center. So if you have the intersection of two Borel subgroups and an automorphism that preserves them, you can find a cartan H inside this intersection, which is x0 stable. This is I don't know. I learned these things from Matsuki in the 1970s, but it's probably older than that. And once you have this cartan, then everything, well, everything starts to look sort of the way that I said somehow. The Cartan involution has to preserve this Cartan, and so it has to act on this Cartan by, well, the basic automorphism that you have up to the normalized. That's, I don't know. I mean, this n delta 0 corresponds to the action of this x0 on this Cartan. That's where the Weyl group element comes from.
Yeah, could you give one example of delta 0 that reserved on the positive root?
Well, so of course there's always the trivial automorphism.
Yeah, so why is
but
that
one other than that, so if you take a product of two of this, I mean G cross G, you can interchange the factors. Right? You have a reductive group with a choice of Borel, the same reductive group, the same choice of Borel. If you interchange the factors, that preserves the positive roots.
So how could we can write out it in n-time matrix?
So maybe the easiest example is well, I won't succeed in writing it, but if you look at the complex orthogonal group, and sort of, I mean, the form is something like x1, y1 plus xn, yn. It's I don't know if that sort of makes sense. Then the automorphism so I write these sort of n by n pictures. I mean the Borel you can take to be upper triangular if you write the
Perhaps
form.
you should take yn, y1 in the opposite order.
You're undoubtedly correct. Yes, or I should have. Anyway, yeah, you're right. That's right. If I want to do it like this, and even then I may have. Anyway,
yes.
I'm getting closer now. Anyway, but this automorphism, which corresponds to interchanging the last two roots of the Vinken diagram of Dn is an example. Sorry?
So some try that you embed this one into A type.
So I can never remember how to do the type A one, but so it's more or less in type A.
An example looks.
You take G to the inverse transpose of G, and you conjugate by this matrix. So taking inverse transpose makes upper triangular, lower triangular, but then if you conjugate by this permutation matrix, yeah, so GLN or something, now it preserves the Borel subgroup.
Other quick questions or remarks? Because we still have, in 20 minutes from now, 3 hours of, no, 2 hours.
It'll only seem like 3 hours.
Yeah. Okay, so let's thank David.